Hello viewers, I am Dr. Saeed. In this lecture, I am providing one more method of solving fractional differential equation by the help of series. This time I am taking a bit different series as you can see on the screen. Okay, I am going to solve this differential equation dy by dt plus d half derivative y over dt half minus 2y square equal to 0, and I am assuming that the solution of this fractional differential equation has of the form y equal infinite series from n 0 to infinity t to the power n by 2 into yn, and I am assuming that the y naught is equal to some constant c. Or taking this assumption, I'm going to solve this differential equation. So what I do, just plug this value of y into series. So this becomes d by dt of y, which is summation from n0 to infinity t raised to power n by 2 into yn, and plus this is the half derivative of y. So I'm taking the fractional derivative of Caputo sense. So instead of writing in this notation, I can also write d half from 0 to variable, which is here t, of y, which is summation n from 0 to infinity t raised to power n by 2 yn, and minus 2 y square, again value of y from n0 to infinity t n by 2 yn to the square is equal to 0. Okay, I just plug the value of y into the series. Now I need to calculate these two derivatives. This is the ordinary derivative, so I can, since this is just a power series, so we can switch the series and derivative, and this only affect this term. So this becomes summation n from 0 to infinity, and when I differentiate t to the power n by 2, it becomes n by 2 t to the power n by 2 minus 1 into yn, plus, and here I need to calculate this Caputo derivative. So the formula for Caputo derivative, as we have seen in previous videos, is d alpha from 0 to t of some t to the power n. It is equal to gamma of n plus 1 over gamma n minus alpha plus 1 into t to the power n minus alpha. This is the formula, and here alpha is of course 1 by 2. So using this formula, this becomes, again we can switch the series and fractional derivative, series from n0 to infinity, and here my alpha is, this is my alpha, which is 1 by 2, and here n is my n by 2. So this becomes sigma n plus 1. So this is sigma n by 2 plus 1 over sigma n minus alpha. So n is n by 2 minus alpha, which is half, and plus 1, and then t to the power n minus alpha. Here it becomes n minus 2, n over 2 minus 1 by 2 into yn, and the last term will remain as it is, minus 2 times summation n from 0 to infinity t raised to power n by 2 yn to the power 2 is equal to 0. Okay. So we can do one more step. We can simplify a little bit the middle term. Everything will remain as it is. So this summation n over 2 t n over 2 minus 1 into yn. Here summation from 0 to infinity. Here's gamma of n by 2 plus 1 over gamma of n over 2, and minus half plus 1 is 1 by 2 t to the power n minus 1 over 2 into yn, and last term again remains as it is, summation t to the power n by 2 into yn whole square is equal to 0. Okay, now we need to expand this series and we can collect different terms involving the fractional powers of t. Okay, now expanding this series, expanding these terms, what I get from the first term, since n is starting from 0 to infinity, so when n is 0, the first term is 0, and since first factor is 0, the whole factor will just 0, and then when n is 1, this is 1 by 2 t to the power 1 by 2 minus 1, so it is minus 1 by 2 into y1, and when n is 2, 2 by 2 1, t to the power 2 by 2, which is 1, 1 minus 1 0, so it is 0, so technically there is no t in this term, or t to the power 0, and then we have y2, and we can do for n is equal to 3, so it is 3 by 2 t to the power 3 by 2 minus 1, which is 1 by 2 into y3 plus so on. So this is the expansion of this first term. Likewise, we can do other term. Here when n is 0, here it becomes gamma of 1 over when n is 0, gamma half, and t to the power minus 1 by 2 into y0 plus when n is 1, this becomes gamma 1 by 2 plus 1, so it is 3 by 2 over gamma when n is 1, 1 by 2 plus 1 by 2 is gamma 1, and t to the power when n is 1, so it is 0, and we have y1, and then for n is equal to 2, gamma 2 plus 2 1, so gamma 2 in the numerator, and in the denominator is 2 plus 2 over 2 1, 1 plus half, so it's gamma 3 by 2, and t to the power when n is 2, 2 minus 1 1, so it's 1 by 2 into y2. We need one more term. When n is 3, it's 3 by 2 plus 1, so it's gamma 5 by 2. So gamma 5 by 2 in the denominator when n is 3, 3 over 2 plus 1 over 2, it's 4 over 2, which is 2, so gamma of 2, t to the power when n is 3, 3 minus 1, 2 over 2, so it's t, and then y3 plus so on. So this is the expansion of second series, and for the last series I have minus 2 into, again it's starting from 0, so when n is 0, it's just t to the power 0, I have only y0, and when n is 1, t to the power 1 by 2 into y1, when n is 2, it is just t and y2, and when n is 3, t to the power 3 by 2 into y3, so on, and this has whole square is equal to 0. Okay, I have expanded few terms of each series, and now I have to collect different powers of t. So as you can see that each expansion have t term having power 0 or power 1 by 2 or minus 1 by 2, but before I do that I need to calculate these coefficients. Gamma 1, as we know that gamma n is n minus 1 factorial, that means gamma 1 will just 0 factorial, which is 1, gamma 3 by 2, and one more, gamma half is square root of pi, and there is one more property, gamma x plus 1 is equal to x time gamma x. Using this property I can write gamma 3 by 2 as gamma 1 plus 1 by 2, which is 1 by 2 gamma 1 by 2, and since gamma 1 by 2 is square root pi, so it is 1 by 2 pi square root. And I have also gamma 5 by 2, so 5 by 2 is written as 3 by 2 plus 1, which is 3 by 2 gamma 3 by 2, which is 3 by 2, and gamma 3 by 2 is 1 by 2 into square root of pi. So using these values, this is 1, this is square root of pi, so we can write this term is 1 over square root of pi, and everything will remain as it is. Gamma 3 by 2 is 1 by 2 per square pi, and gamma 1 is 1, so this coefficient is actually 1 over 2 square root of pi. And for here, gamma 2 is again gamma 1, gamma 2 is equal to 1 factorial, which is 1, and gamma 3 by 2 is 1 over 2 square 2, and when we simplify, 2 becomes in the numerator, so it's 2 over square root pi, this coefficient. And here gamma 5 by 2 is 3 over 4, and gamma 2 is again 1, so this coefficient is 3 over 4 pi square root. So this is the simplified coefficients we need to use when we compare the powers of t. Okay, now first I will collect power t starting from negative 1 by 2. Okay, which terms have t to the negative? In the first expansion we have 1 by 2 y1, so it is 1 by 2. Okay, I use to get it more clear and use the same color. So mine it's on the first term I'll get 1 by 2 and y1. In the second term I have this power t minus 1 by 2, and its coefficient is 1 over square root pi times y naught, so it is 1 over pi square root into y naught. And for the third series I do not have any term involving negative half, so this is equal to, since right hand side is 0 for every t, so it's just 0. Okay, this is for t negative 1 by 2, and now I will collect t to the power 0, the term which doesn't have t term. So on the first we have this y2, so here I have y2, and the second expansion, the coefficient of t to the power 0 is 1 over 2 square root pi into y1, so this is pi square root over 2 into y1. And in the last expansion there is only one term which is free from t, which is y naught, but remember we have a square, so this becomes, when we expand this term, this becomes y square, so it's minus 2 y naught square, minus 2 y naught square is equal to 0. And for the third we compare t to the power 1 by 2. Okay, from the first expansion this term contains t to the power 1 by 2, we have 3 by 2 y3, so we have 3 by 2 into y3. And for the second expansion we have this term which have t to the power 1 by 2, so becomes 2 over square root pi into y2, 2 over square root of pi into y2. And for the last expression we have this t to the power 1 by 2, but remember we have a square. When we expand, this term will have a power 2 which turns into the power 1, so this is no longer t to the power 1 by 2, and you can see that there is no term in remaining expansion which have power t by 2 after this expansion. But remember, when we take square we have few more terms like 2 times and product of each pair. So when we will pair the first two terms, 2 times this term and this term will contain t to the power 1 by 2. So it means when we expand this series we will get only one term which have t to the power 1 by 2, and that term is 2 times y naught into y1. So this becomes minus 2 is outside, and 2 y naught into y naught, y1 is equal to 0. So this is the total terms that we have for t to the power 1 by 2. Okay, now we have to solve these equations to get our components y naught, y1, y2, so on. And remember we have y naught is equal to c. We have given this first component. Using this component and first equation, I can readily find 1 over 2 y1 plus 1 over square root pi into y naught, which is now c is equal to 0, and this becomes 1 by 2 y1 is equal to minus c over square root of pi, and finally I have y1 which is minus 2c over square root of pi. This is my second component y1. Okay, in the same way, now I will take this equation y2 plus square root of pi over 2 into y1, which have this value minus 2c over square root of pi, and minus 2 y naught square. Since y naught is c, so it's 2c square is equal to 0. This cancels out, this cancels out, so I am left with y2 minus, here I will just have c, and then minus 2c square is equal to 0, and finally y2 is c plus 2c square. This is my third component. Moving on, for the third equation, this one I have 3 by 2 y3 plus 2 over pi square root into y2, which have 2c square plus c, and minus 4 into y naught, which is c, into y1, which have minus 2c over square root pi is equal to 0. This becomes 3 over 2 y3, and I'm shifting everything on the left hand side. Right hand side, this becomes 2 over square root of pi minus 2 over square root pi into 2c square plus c, and then minus 4 times 2 8 c square over square root of pi. So I can take LCM, which is pi square root, and here becomes minus 4c square and minus 2c and minus 8c square, which is minus 12c square minus 2c over square root of pi. So y3 becomes 2 over 3 into minus 12c square minus 2c over square root of pi, which can be written as, after simplification, this is minus 3 4s are 12 and 4 2s are 8. So 8c square over square root of pi, and then minus 4 times 2, 2 times 2 4, 4 over 3 square root of pi into c. So this is my y3. So y3 is minus 8c square over square root of pi and minus 4c over 3 times square root pi. This is my fourth component, y3. Okay, now I have got enough components. So since my assumed solution was y is equal to summation n from 0 to infinity t to the power n by 2 into yn, which can be written as y naught plus t to the power 1 by 2 into y1, t to the power 1 into y2, t to the power 3 by 2 into y3, plus so on. And this becomes y naught, which is c, plus y1, which is minus 2c, minus 2c, minus 2c over square root of pi t to the power 1 by 2, and then I have y2, which is 2c square, y2 is plus 2c square plus c into t to the power 1, and then finally y3, which is minus 8c square over square root of pi minus 4c over 3 times square root pi into t to the power 3 by 2, and so on. So this is the solution of the given fractional differential equation. Of course, this is as an infinite series. Apparently it doesn't have any closed form. Okay, in the next lecture I will solve this very differential equation, this fractional differential equation, by the help of Adamian decomposition method, and we will see that using that Adamian decomposition method we will achieve the same solution as well. Thank you for watching.